Welcome back to the show. Today, we're exploring the intriguing realm of distributed systems with a particular focus on a key concept, total order broadcast. If you've ever wondered how systems ensure that user accounts are uniquely identified or how they maintain consistency across multiple nodes, you're in the right place. We'll break down the complexities of this topic, looking at the challenges that arise when ensuring unique usernames in a distributed environment, as well as the mechanisms that help us achieve that. So let's dive in. Let's start with a common scenario in distributed systems, creating user accounts. Picture two users trying to register with the same username at the same time. The system needs to ensure that only one of them succeeds while the other fails. This is where total ordering comes into play. At first, using something like Lamport timestamps might seem like a straightforward solution. The idea is simple. If two usernames conflict, the account creation with the lower timestamp wins. However, this method has its limitations. While it can help determine outcomes after the fact, it doesn't work well for real-time decision-making. When a node receives a request to create a username, it doesn't yet know if another node is also trying to process the same request. Without that information, it can't confidently declare which operation should succeed. Now, let's dig deeper into the implications of relying solely on timestamps. The system would need to check with every other node to see if it's in the process of creating an account with the same username. This creates a significant issue. If one of those nodes is down or unreachable due to network problems, the entire system could grind to a halt. Clearly, this isn't the fault-tolerant system we want. So what's the solution? To implement a uniqueness constraint for usernames, we need more than just a total ordering of operations. We also need to know when that order is finalized. If a node can confirm that no other operation can insert a claim for the same username ahead of its own, it can safely declare the operation successful. This brings us to total order broadcast, also known as atomic broadcast. It's important to clarify that this term can be a bit misleading. It doesn't refer to atomicity in ACID transactions or atomic operations in multi-threaded programming. Instead, it describes a method where messages are delivered to all nodes in the same order, ensuring consistency even in the face of faults. Achieving total order broadcast in distributed systems is no small feat. It requires all nodes to agree on the same order of operations, which can be tricky. While we've previously discussed using timestamps or sequence numbers, these methods don't provide the same level of robustness as single-leader replication. In that model, a designated leader sequences all operations on a single CPU core. But this approach raises concerns about scalability and failover if the leader goes down. Partition databases, which often have a single leader per partition, typically maintain order only within their partitions. This can lead to inconsistencies across the entire system. Achieving total order across all partitions requires additional coordination, which complicates matters even further. Now let's talk about the safety properties that total order broadcast must satisfy. First, messages must be delivered to every node in the same order. Secondly, these ordering properties must hold even if a node or the network experiences faults. While messages may not get delivered during an outage, the system can keep retrying until the network is restored, ensuring that messages are eventually delivered in the correct order. This connection between total order broadcast and consensus is crucial. Total order broadcast is vital for database replication because if every message represents a write operation and all replicas process those writes in the same order, consistency is maintained. This principle is known as state machine replication, which we'll explore further in a future episode. Let's visualize total order broadcast as a log. Each message delivered is like a pending to this log. And since all nodes must deliver the same messages in the same order, they can all read from the same log and see a consistent sequence of messages. This becomes particularly useful when we consider fencing tokens, which help manage concurrent operations. Each request to acquire a lock can be appended as a message to the log, with a sequential number serving as a fencing token. You might be wondering how total order broadcast relates to linearizability. While they aren't the same, there are strong connections between the two. Total order broadcast is asynchronous, meaning messages are guaranteed to be delivered reliably in a fixed order. But there's no guarantee about when that delivery will occur. In contrast, linearizability provides a recency guarantee, ensuring that a read operation sees the most recent value written. For instance, to ensure that usernames uniquely identify user accounts, you can use an atomic compare and set operation. When a user attempts to create a username, the system checks if it's available. If two users try to claim the same username at the same time, only one will succeed, thanks to the linearizability of the operation. So, how do we implement total order broadcast using an append-only log? Here's a simplified process. First, append a message to the log, tentatively indicating the username you want to claim. Next, read the log and wait for the message you appended to be delivered back to you. Then, check for any messages claiming the username you desire. If your message is the first for that username, you can commit your claim and acknowledge it to the client. If another user's message comes first, you abort the operation. This method ensures that all nodes agree on which write operation was committed or aborted, maintaining consistency across the system. However, while this guarantees linearizable writes, it doesn't automatically ensure linearizable reads. If you read from a store that's asynchronously updated from the log, you might end up with stale data. To achieve linearizable reads, you have a few options. You could sequence reads through the log by appending a message, reading the log, and performing the actual read when the message is delivered back to you. Alternatively, you could query the position of the latest log message in a linearizable way and wait for all entries up to that position to be delivered before performing the read. Another option is to read from a replica that is synchronously updated on writes, ensuring it's up to date. In summary, total order broadcast is a powerful mechanism that underpins many aspects of distributed systems. It ensures consistency and fault tolerance, allowing us to manage operations like username creation effectively. While it may seem complex, understanding these concepts is crucial for anyone looking to work in the realm of distributed systems. And that wraps up our exploration of total order broadcast in distributed systems. We've covered how it helps maintain unique usernames, the challenges of achieving consistency, and its relationship with linearizability. As we continue to navigate the world of distributed systems, these concepts will be vital for building robust and reliable applications. Thanks for tuning in, and be sure to join us next time as we delve deeper into the intricacies of distributed computing.